Welcome back to elementary statistics. In this video, I want to look at confidence intervals for proportions. As we've seen previously, when we talk about proportions, we are looking at a binomial distribution where every outcome can be classified as success or failure. So we're taking all of the possible outcomes for the experiment and we're splitting them into two groups, the success group and the failure group. We have the probability for success, we're calling P, and the probability for failure, we are calling Q. We also looked at a specific experiment where we had N trials and X successes. And then the proportion of success we denoted as P hat and calculated that as X divided by N. The proportion of failure we denoted as Q hat. And one last bit of calculation. The probability of failure has to be 1 minus the probability of success, and the proportion of failure has to be 1 minus the proportion of success. Again, that comes from the fact that we are looking at a binomial experiment. Binomial, two names or two categories more generally. There are only two possibilities. Everything has to be either success or failure. And we learned how to do some calculations involving these. And at the end, we realized that these ideas of proportion of success and proportion of failure look like they should be very good estimators for the probability of success and the probability of failure. All we need is a slightly better way of talking about the mean and standard deviation, which fortunately is very easy to come by. I know that the expected value or the population mean for successes is the number of trials times the probability. So that is approximately my value of X. And I know that if I take X and divide by N, I get P hat. So yes, mathematically we can say that the proportion of success P hat is a good estimator for the probability of success. We also know that the standard deviation was calculated as the square root of N times P times Q. But again, we are changing our scale, which means that the standard deviation is going to change as well. We're going to take that standard deviation, we're going to divide by N. Using a fairly simple mathematical trick, N is the same thing as the square root of N squared. And some of those N's cancel out. We get that the standard deviation for P hat should be something on the order of PQ over N, all underneath the square root. I am going to make one last approximation here. I claim that I can simply substitute in p hat q hat over n instead of pq over n. The way that p and q are related to each other means that numerically, p times q and p hat times q hat are going to be very close together. And when we take the square root, they're going to be even more very close together. So this calculation, this difference, isn't going to be substantial as long as we have a representative sample. To get an idea of what I mean by that, let's just take a couple of values here. If p is 0.5, then q has to also be 0.5. And if you multiply those numbers together, you get 0.25. If we make p just ever so slightly smaller, okay, not ever so slightly smaller, a good bit smaller, 0.4, then q has to be 0.6 because p and q together have to add up to be 1. And if you multiply 0.4 times 0.6, you get 0.24. Now, it's not at all going to be the case that as you go through this, moving the probability by 10% is going to result in that little 1/100th before you take the square root of a difference between the resulting value. But I think that's a good illustration of why if p hat and q hat are near p and q, then because of the mathematics of decreasing p increases q by the same amount, the numbers are going to be incredibly similar. We can treat them as basically the same, and it gives us a nice value to work with. And so, since we have normally distributed data, we have a mean and we have a standard deviation. I can use the z-score as a way of constructing a confidence interval. P has to be equal to p hat plus or minus your z-score for your given confidence level times the square root of p hat q hat over n. So let's look at something that we can work with pretty reasonably. Let's say that we are, excuse me, let's say that we are surveying the students in a particular mathematics course and asking them very simply, is this the last mathematics course that you're going to be taking? There are 36 students in that particular math course. And of those students, 25 said that that was the last math class that they were going to need to take. And using just that information, I would like to construct a 95% confidence interval for the probability of a student taking this course anywhere, it being the last math course they were going to take. Well, given n and x, I can get that p hat is 25 over 36, and I'm just going to leave that as a fraction. I find that that's going to make it so that I can punch things into my calculator a little bit more easily. If I did the division now, I would have to round, and then things might turn out to be a little bit of a mess. But I do know then that q hat If 25 of the 36 students said that this was the last mathematics course that they had to take, then there are 11 students left in that class of 36 who are planning on taking at least one more math course. I also know that if I have a 95% confidence interval, I can look that up on my z-score table, or you just know offhand, right? 90%, 95%, 99% are almost always the confidence level that we're going to be talking about. For a 95% confidence level, that means that z is plus or minus 1.96. And yeah, that plus and minus and that plus and minus is in fact the same plus or minus, but I would rather keep writing it down and remind myself that it's a thing that I have to worry about. All right. And that's everything that's in the formula. My estimator for p is p hat, 25 over 36, plus or minus z, which is 1.96, times the square root of p, which is 25 over 36, times q, which is 11 over 36, all over n, which is 36. All right, maybe I'll do this calculation in a couple of separate steps. I'll start with the multiplication in the numerator underneath the square root. So I have 25 divided by 36 times 11 divided by 36, which is going to give me an ugly decimal number. I take that number and I divide by 36, and then I take the square root of the previous answer. On my calculator, I have this really nice ANS, which means take the previous answer. I can punch that into my calculator. I can get everything all in one go. And I get that the square root in question here is 0.075. I'll round that up to 0.758. I'll take that number and I'll multiply times 1.96. To get 0.150. Now also I will take the 25 divided by 36, write that as a decimal as well. It is 0.694. And if I take the minus branch, 0.694 minus 0.150, I get 0.544. And if I take the plus branch, 0.694 plus 0.150, my calculator tells me that side is 0.844. That's a fairly wide confidence interval when we're talking about probabilities, right? This is somewhere between 54 and 84%. I don't know about you, but for me, somewhere between 54 and 84% doesn't seem to narrow things down all that much. So let's take a look at things from a different perspective. The confidence interval that I just constructed was entirely too large. I want to take enough samples that my confidence interval is down to plus or minus 2.5% with a 95% confidence. Well, that means that I need the 2.5% to be equal to the plus or minus part of the confidence interval formula, z times the square root of p hat q hat over n. And one of the things that you hopefully notice in this formula is that we've got a lot of unknown here. P hat is unknown, Q hat is unknown, and of course, N is the thing we're trying to solve for. There are two ways that you can fill in some of that information. If you have a previous study, like we have, you can use those values as an estimate for p hat and q hat and assume that they're not going to change all that much, even though they probably will change at least a little. If you don't have a previous study, the absolute largest number you can get out of p hat times q hat comes when p hat and q hat are both 0.5. If you make p hat larger, q hat will become smaller in such a way that their product is smaller than what you get if you multiply when they're both 0.5. And so that will give you the worst case scenario. The worst case scenario always overestimates the number of samples that you need, but something like this will always work. All right, so fill in whatever number you have instead of 2.5%, but I want to get within plus or minus 2.5%. That means that there's a 5 percentage points difference between the minimum and maximum in my confidence interval. So if I divide both sides of this equation by z, and then I square both sides of the equation. All right, at this point, I finally need to convert. 2.5% is 0.025. Then I'm going to take the reciprocal of both sides of this equation, z squared over 0.025 squared. And yeah, I'll use my calculator here. 0.025 squared is 0.000625. And then finally multiply by p hat and multiply by q hat. Again, if you don't have a previous study to go on, you can use p hat and q hat are both 0.5. But because I'm trying to do a follow-up to the study that I just completed, I shouldn't have scrolled that quite off of the screen. I know that p hat times q hat was something on the ballpark of 0.2122. Right? I calculated that in my earlier work. And I know that Z is still 1.96 because I'm looking at a 95% confidence interval. All right, 1.96 squared is 3.8416. So if I take 3.8146 and I multiply by 0.2122 and I divide by 0.000625, my calculator tells me that I get 1,304 point some little bit more than that. I'll round that up and call it 1,305 because getting too many samples is going to be what we need. Getting too few samples will be a bit of a problem. All right. So to get my proportion down to a 5% window, plus or minus 2.5%, I need over 1,300 samples in this particular case, which I'm not going to get from just one class. I'm probably not going to get from just one school or just from one semester. But if I tried hard enough, I could collect data over time. I could collect data at several schools, and I could get that large of a sample, and I'd be able to go from there. All right, that's all I have on this video. So thanks as always for joining me, and I'll see you next time.